can leave us up to be on the back track.
Okay. All right, guys, please quiet down. We're getting started here. I actually talked to quite a few of you guys individually yesterday about this last step on 13, where you so a lot of you guys got to like the last, what, it was 13, right?
Yes.
Okay. So derivative, okay, 1 times y plus y prime times x equals 1 plus 2y times y prime, okay? Hopefully that's getting a little bit easier by now, that process. So if you rearrange this, you get something like y prime x minus 2y prime equals 1 minus y. After you factor out the y prime, you can divide both sides by that expression, and you get this. Okay. Now, so then this last part can be pretty confusing because you go, well, I could tell you where, say, like the tangent line is horizontal. That's pretty easy, right? That would be any place where the y value is 1. You can set that equal to 0. And what do you do with that? You take that y equals 1, you plug it in up here and see if there's a solution. Which I don't think there is. Is there if you did plug in 1? Because you'd have x equals x plus 1, which is clearly not possible. Okay. But maybe this vertical line. So what you do is you say, well, to be a vertical tangent line, you'd have something on the bottom that's the bottom would be 0, right? Mm-hmm. So I'd say, okay, I guess in order for there to be a vertical tangent line, we know that the quantity x minus 2y. So if you think about it, this is actually a system of equations, right? Because the point that we're looking for, remember the question says find all points where the curve has this property. So the point has to satisfy 2 different conditions. The first condition is it has to live on this curve, right? So its x value and its y value have to satisfy this, meaning the product is equal to the sum of the x value and the squared y value. And then it also has to satisfy this condition because of the derivative equation. So as you guys know, right, if you have 2 equations and 2 variables, most of the time you can solve. So anyway, let's do that. So let's solve the system. Probably the easiest way is to write this and then do a substitution into that. So it's so artistic, right?
Mm-hmm.
So it's going to be 2y times y. Notice I replaced that x with a 2y equals 2y plus y squared. Everyone feel okay about that substitution? Okay. 2 banana. I don't know why am I like writing down a whole step just is taking y times y and writing it as y prime. I don't know why I'm doing that. Seems like more than it needs to be. Okay, anyway, so 2y squared minus 1y squared is y squared. Subtract the 2y over. And then, of course, you solve this. You get the 2 y values, right?
Mm-hmm.
Is that the answer?
No.
No. Those are just the 2 y values where we might possibly see a vertical tangent line. So now we got to take those y values and say, what would be the x values that go with that on this curve? Or maybe you could just think simpler and just go, well, according to this, the x value is just going to be double the y value. So those are your 2 options for solving for the x value. You're probably going to go with the latter, right? So what's the x value that goes with this y value?
No.
0. So 0, 0. Then what's the x value that goes with this y value? 4. And there's only one more thing. We have to make sure that those points actually are on this curve. So you have to kind of make sure they satisfy both. So does 4, 2 work? Yeah. Does 0, 0 work? Sounds a bit easier. But yeah, so the answer is those 2 points. And then let's check our answer as we like to do. Mr. Hooter, x times y equals x plus y squared. Oh, it's hyperbolic. Cool. There's 4, 2. We can see pretty clearly that there's going to be a vertical tangent line there, and then there's the origin. Yay!
Yay! Booga
Yeah.
booga.
Booga booga.
My favorite thing.
Is that
in the
from
world-
Crash Bandicoot?
No. My favorite thing in the world is
Mask.
my dad and I were talking, and he was like, "I don't believe in that hooky pooky."
Got him. Got him.
Don't
believe in that.
Sounds
like something my grandma Jay would say.
I mean, he was like jokingly making fun of something, but it was just the funniest
George.
thing I've ever heard. Making fun of that hoopy poopy. I don't believe in that hoopy.
So
Now I use hoopy poopy all the time.
yes, the next thing I want to discuss with you guys is so 14, 15, 16, 17 are all kind of the same idea. It's just additional practice with that technique. If you look at 19 though, 19 is kind of a different
18's a
Have a
long
question?
way.
It's a second derivative.
Oh,
Oh, in terms of why only.
Yeah, so let's before we do any calculation, let's talk about this question just like kind of holistically here. There's a curve. In this case, I gave you this one of the simplest curves we know about, which is what? This is a circle. So a circle, and then the question's asking, can you write a formula for this? By the way, does anyone know what this is? The slope. What's this? Concavity. So we've already done the slope problem, right? There's a formula that tells you the slope on this circle, the slope of a tangent line, given any xy pair. What this question's asking is, can you write a formula for the concavity of the circle that only depends on the y value? Does it make sense why that actually is possible to begin with? How like just so pick a point on here.
Yes.
Because of the symmetry, all that really matters is the y value. Are you high up on the circle or are you down low on the circle? Because are we concave up or concave down here?
Concave down.
Concave down. But if the y value is negative, you'd be
Smiley boy.
concave up. Now, an interesting question is, what do you think the concavity is here, and maybe what about there?
Well, it's still
would there
concave
be?
down on the top, and then it's not. There's no concavity there.
Yeah. The answer might surprise you. What, Alyssa? Okay. I was just saying it's not obvious because it goes, you're concave up and you're concave down. So either you're going from positive to negative by passing through 0,
Oh, it's a minute.
or maybe it's some kind of asymptotic behavior. And if we're asymptotic, that would mean that you're getting like enormous concavity values close to the x-intercept. But anyway, let's get into the calculation. So the first part's going to be nice and easy peasy. This is 4, by the way. Radius is 4. Derivative 2x plus 2y, y prime equals 0. Cool beans? Okay. And so let's rearrange that. Okay, so that of course tells you things like, oh, if x is positive and y is positive, the slope is negative, which we can see that's. So what next? Let's get the second derivative, right? That y prime is the slope. So let's take the second derivative, which would be y double prime. So the derivative of y prime is y double prime. What rule do I have to use here?
Quotient.
Quotient rule. So I got to go derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So there's the bottom squared. The top's going to be -1 times y minus y prime times. Everyone okay with that? So getting a little, because that is not a terrible answer or anything. What it tells you is that your second derivative at some point is let's maybe factor out the negative sign. Or actually, we got basically negative y plus x times y prime all over y squared. So if you tell me a point, an xy pair, then I could calculate the slope and then plug the x, the y, and the slope into that formula, and that would tell you the concavity. Make sense? Okay, but the question gives us a big hint as far as like you have to find a way to get this in terms of just y. So who's got an idea?
So it should be
A sub?
yeah, substitution.
Can we sub? Yeah, so this, we don't want y prime in there.
You know why it's not just saying what?
Yeah, let's replace that y prime with that. Is that okay? Make sense?
Yeah.
So y double prime would be negative y plus x times negative x over y. All right.
Did we?
The y squared.
Y squared.
The bottom.
Just testing.
Yeah.
Okay.
Obviously.
Thanks. Okay, so now, we got fractions inside our fraction. So don't forget your
No.
corporate sponsor, Johnson and Johnson's. No more tears. How will I get rid of that? That makes me cry. Got a fraction in the fraction. You multiply it by
Y over
y over y.
Got a fraction in the fraction.
Okay, so you have y times. If it's okay with you guys, I'm also going to factor out this -1
Yep.
and put it out front like this.
I guess.
So there's a negative and a negative, so you can factor out that negative. So now it's going to be y times y is y squared. And then x times x divided by y times y makes
X squared.
x squared, not negative because we factored out the -1 already, but yeah. So, and then the bottom is y cubed. Okay, we were so close.
What does it have?
Who sees it? Anyone? Do you see? Rafe, do you see?
Y squared plus x squared is 16.
Oh,
But it said it's
but-
equal to 16, right?
True. I agree with you, but how about just noticing that this is 16? Same idea, right? What did Trey say? Sorry.
I said that's
Exactly
why I
what
said-
you
Oh, I'm
just
sorry.
said.
My bad. But yeah, so you're totally right. You could have done that, or been like, oh, x squared plus y squared. If you live in the circle, which we're assuming you do, then your x squared plus your y squared is 16. So
I would assume.
look at that. Like, that's incredible.
Wow.
Well, that means that 0 is extraneous solution.
Well, yeah, what this tells you is that as y approaches, so it tells you basically as y approaches 0, the concavity approaches infinity. Well, plus or minus infinity, depending on which direction you're coming from. Which is kind of fascinating, I think. Like, this point here has some enormous positive concavity. And it also tells you, I was kind of expecting the concavity here to be 0, but if you plug in, say, -4, it's actually just 1/4. It's maybe kind of a surprising number. So the concavity at the bottom or the top of the circle is just going to be 1/4 or -1/4.
So basically you were wrong. Lame.
Wrong, sad.
I'm just
Capital
kidding.
SAD.
Just kidding.
But you guys see what this hopefully makes good intuitive sense, just as far as every time y is positive, the concavity is negative. So you can see that at the top of the circle, we say whenever y is positive, the concavity is negative, and then whenever y is negative, the concavity is positive. Happy circle man.
Yippee!
All right, should we do one more?
Sure.
One more?
I would say, I think so.
Jersey.
Jersey.
And then I want to get into related rates a little bit, which is the same idea. It's just this, but with a little bit.
Rates.
Huh?
With the rates. And judgment.
This is all rates, right? Y prime is a rate. It's how is y changing with respect to a change in x.
Great with rates.
Oh, man, I forgot about
What?
Brady, the math cat. The cat that's great with rates.
What's that from?
It's Brady the math
Is that from a movie?
It's a little math show on YouTube. It's
I
really
was made for love and the ratios were you made for love and
Sounds awesome.
Flashback to
The sixth grade.
Yes, yes.
Jesse,
Thank
be
you, Mrs.
careful.
White.
You can't sing.
What?
You can't sing in your house.
Oh,
Yeah, I told him about how we're not allowed to sing because, bad for our voices.
That's your voice?
Yeah,
It
Miss
is
Ackthorn
true,
banned
my
us from
voice
singing.
She hasn't banned us from singing. We're just
In
not
class.
singing in class right now.
Okay, so here's
Vocal
number
class.
20 will be another example of this.
I mean, I cannot agree.
You guys take a minute on your own. Just try to take the derivative of this. Give you a minute or two, and then we'll make sure we all got the same answer, and then from there, then we'll proceed from there.
Whoops.
Well, now.
No, done. Jesse. That's stuck in my head.
Which one, Rady or
The other
I was
one.
made for loving them ratios?
Yes.
Oh yeah, kiss. They'll always be there. I was made for loving you, baby. Made for loving you. Classic. Truly.
No, I don't want
Please stay.
It's the prettiest A I have ever made. Look at that. Look at that A. That's a good A.
Yeah, that is a good idea. Beautiful.
Unintentional.
And a very unusual. No, this is wrong. Hold on.
Welp.
That was incorrect, Jesse. No, I just did it again. Okay, that one.
Okay. Can we all get? Don't wait.
We're getting there.
Well, I'm gonna try to teach you how to do it, not just tell you the answer, ideally, but here you go. So 2y prime plus y prime equals 3x squared. So if you factor out the y prime and then divide, I might just skip a little step here if that's okay. You'd have 2y plus 1 left over. Okay, so did we all at least, the very minimum, get this far?
Yeah.
Okay. So now, let's take the second derivative, or take the derivative of both sides again with respect to x. So the derivative of y prime is y double prime, and the derivative of this, again, we gotta use the quotient rule. So it's gonna be 6x times 2y plus 1 minus 2y prime times 3x squared. Is that everyone okay with that? Quotient rule?
Yes.
And the bottom is 2y plus 1 squared. We're all, any questions on that application of the quotient rule?
No. Think.
You can take some time to think.
No, I got that far.
Okay,
We good.
sweet.
We good.
Now, it's kind of up to you. Do you want to do a substitution now or do a substitution? Let's take now. Okay, that sounds good because keep in mind, guys, it says that we're looking for the equation in terms of x and y. So there's really only one pesky term we got to think about. In the previous question, we had to make that sneaky substitution of getting rid of the x's as well. So the x squared plus y squared equals 16 came in. But here, I just need to get rid of this dude. Okay, so let's just replace him with that.
Oh, that's disgusting.
This will kind of test our algebra skills. So, there's going to be, hello,
Yeah.
Hi, there's something for Alyssa and Laura.
or back corner over there. So there's a banana.
Uh-oh.
This is going to have a 1 over banana. And there's a banana squared at the bottom. So think of that as one little parcel of information. That make sense what I'm talking about?
Yeah.
Okay,
Yep.
so
Yeah.
this is going to be so 6x times banana minus 2 times this. So I could write that as, well, how about this? 2 times 3x squared over 2y plus 1. Is everyone okay with that?
Mm-hmm.
So that's just the same as that, but the y prime is replaced by this expression here.
Mhm.
And the bottom is still just 2y plus 1 squared. And then you guys all see like the sort of the structural similarity between this and the last one, where you got a fraction inside a fraction.
Yeah.
You want to get rid of that, and so you're going to multiply by 2y plus 1 over 2y plus 1. Okay. So this times this would be 6x times 2y plus 1 squared, right?
Mm-hmm.
Banana divided by banana makes 1. So what's left over after this term gets multiplied by this?
18.
2 times 3x.
Well, yeah, 2. So 2 times 3 times 3 is 18. X squared times x squared is x to the 4. So I think probably the best way to write that.
Yeah.
And the bottom is banana squared times banana, which makes banana cubed.
That's it.
Wow.
Well,
Lovely.
you could ask the question, is there any way of making this look nicer?
Or you could just be like, that's good.
Messy hair, don't care.
That's a good, I don't care.
Well,
I think Jesse lives by that.
I do live by that rule.
No, you should always ask yourself, like, can I simplify this? But, well, okay, this term has no y's in it. This term does. So there's obviously nothing you can factor out of the whole top. Yeah, I guess that pretty much settles it there. If there's no way to write this top in a more like neat, nice way that I can think of. So there you go. And then the question just said in terms of x and y. So that what this shows you now is it's kind of a complicated thing, but if you can tell me a point that lives on this curve, we can just plug that xy pair into this, and that'll tell you the concavity of the curve. Okay?
Woohoo!
Woohoo!
Wait, what? Why'd you laugh? I'm genuinely excited about this.
I appreciate it.
Because you're genuinely excited about
All right.
it.
All right, so shut up, Ahmed. Get out of here.
I only speak the truth.
I know, but why would Jay Hall want to? He's also genuinely
You're very
excited.
because you're very entertaining, Jesse.
Oh, good. I'm
Because you're so
glad.
lit.
Oh, good. I'm glad. Good. I just
Okay,
thought
so,
my eye was sarcastic.
we'll have some work time tomorrow because I want to just cover related rates today. The basic idea is very simple. It's the exact same thing we've been talking about. We're actually about to have a reduction in complexity because this is a fairly convoluted problem, kind of about implicit curves. But anyway, so number 22. Let's just get into it. You got a square whose
I just want the drip.
whose side length is increasing at a rate of 3 feet per minute. And then what you're being asked here is, what exactly can we conclude about this at a certain moment in time? So you guys can all imagine an expanding square, right? Just imagine a square and it's growing.
Yeah.
Now this question says that. Good question. You don't need to know that, but you could certainly for this particular problem assume it was starting off with like basically 0 area. But what you're going to find is you actually don't need to know like earlier information about the system to make some conclusion about it. So here's my square. A square has a length and a width, but they're the same number. So I'm going to use x. Okay? X by x squared. So there's a word in here that tells you what our variable is going to be. I'll give you a hint. The variable is not x. X is going to end up being a function. So I think I know the answer to this. X is a function of minutes of time. Yeah, exactly. Because it's sort of a rule of thumb when you're doing this stuff. If a question mentions time, mentions minutes, there's a really, really, really good chance that your problem's going to be time is your variable. Okay, so t is going to be like your variable. So then what are we taking the derivative with respect to? T, time. So, all right. So what we can say is that when this says the length is increasing at 3 feet per minute, you can translate that sentence into the change in side length with respect to time is 3. So, which we usually would write that as just like this, x prime equals 3. Are there any questions on the underlying logic here? Yes?
Is it like each side or just one side?
The whole square. So good question. Yeah, the way this is worded, assume the square is, continues to be a square. Soon we'll do a question where it's a rectangle and like say the base is expanding at a different rate than the height, And you can talk about, well, how much is the area changing, so. So we're gonna assume this thing stays a square, so, but as far as notation goes, this often confuses people, because up to this point, most of the time, we're talking about like dy over dx. Now we're talking about, yeah, so what this is saying is if you were to graph, how does the square side length change over time? The slope is 3.
Yeah,
That make sense?
yeah.
Mhm.
Some people get the x annoys them so much they'll make this like an L or an A or a B or something, because then I don't know, that just makes it like, or even a Y makes them feel less confused. But okay. Anyway, the first A says at what rate is the square's perimeter increasing? So what you do for a question like that is you start off, you write an equation for the perimeter. Say perimeter is, what's the perimeter of the square? 4x. Great. Well, the question's asking, what's the derivative of the perimeter? At what rate is the perimeter increasing? So you'd say p prime, and by the way, p prime means the change in the perimeter with respect to time. Would be what?
4x times.
Yeah, this is the confusing part, right?
Yeah.
So x is a function of time now. You gotta think of this value as a function.
Makes sense.
If we had said dp over dx, that would be 4. But since it's dp over dt, you're basically using the chain rule. So now what do? You say, well, we know that x prime is 3, so what's the answer to this question? 12. And this question has units, so you probably should put units. This was feet. The perimeter, of course, would be in feet, and the time unit we've been using is minutes, so feet per minute. Okay?
Yep.
That make sense?
Mhm.
Well, I want to watch Mary Poppins.
Random.
Okay. For part B, by the way, I mean, does this answer does it seem like really simple?
Yeah.
If you make, like if the square went from say 15 by 15 to 18 by 18 over a 1 minute period, well, you would have added 12 to the perimeter, right? So pretty simple.
Yeah.
The area is a little bit more complicated because, yeah, the bigger the square is, the faster the area grows. So the area of a square is x squared.
It's 2x.
Okay, are there any questions on that there?
Nobody knows.
You gonna make it, Bailey? You gonna survive? Okay. Sorry if it's boring. All right, so
So that could be simplified just to 6x.
right, so now here's some notation. The question specifically says, what's at the moment when the side length is 15? So what you do is you say, I'm evaluating a prime at the moment
When x is 15.
when x is 15. So then what you're doing is you gotta plug in 15 for x, and you gotta plug in 3 for x prime. And so you get 90. 90 what?
Square feet.
Square feet per minute. So this is something I'm actually very curious of how intuitive you guys feel this is, but if you take a big square and you add 3 feet to all the sides, it's gonna grow a lot more in area than if you did that to a tiny square.
Yeah.
Mhm.
I'll give you a simple example here. If you go from like say, go from a 6 by 6 to a 9 by 9, and then go to a 12 by 12. So notice I added 3 every time, but we went from 36 to 81 to 144. That jump is a lot bigger right, than this jump.
Yeah.
Okay, so that's why this x is showing up. So the bigger the value of x, the bigger your a prime is going to be. But notice that was not true for perimeter. Kind of interesting. Did I ever give you guys that problem about the putting a belt around the earth?
Yes.
I did not.
That's that
like
idea. Is
problem.
like if you take an enormous circle and you add a little bit to the radius, it doesn't matter how big the circle is. It's always going to have the same change in circumference. But if you add a little bit of radius to a big circle, the area changes bigly.
Bigly.
Just drop,
Yeah.
can you take the derivative of the area equation to find like the rate of change?
Something inside.
Yeah, that's what we're doing here because
Okay, I guess you just graph. Okay.
Then what would it be if
Yes.
you took it again?
what?
If you took it again, what would it be? Just out of
So the
curiosity.
second derivative of a would be the rate of change of the rate of change. So it would be square feet per minute, which is maybe a little
Would
bit harder.
anybody ever need that?
It's analogous to acceleration. It's like saying, oh, my position is in feet, or say meters, and my time in seconds. My speed is meters per second, and my acceleration is meters per second per second. So I think, yeah, there might be some context where you wanted that for an area quantity.
Jumps into physics, but message changes of distance because Americans don't. He said feet, and it was like, oh, can't do that.
No,
It was something.
no.
I like feet. Yeah, feet. For a lot of things, I think in terms of feet. Some things meters. Just depends on what it is. Okay, let's do 23. It's a cube this time.
Uh-oh. It's shrinking now.
Here it is. Okay.
Okay, I'm just curious about your thoughts on this, J-Hall. So when you imagine a square expanding at 3 feet per minute in the length, how do you imagine it growing? Do you imagine it like staying, like the center will be fixated in the point, or one of the corners will be fixated in the point as it grows?
I'd probably consider the bottom left corner to be at the origin and fixed, and the rest. That's a good question, though. Yeah, I wouldn't consider it expanding in all directions, but I could see that would make sense too.
I was just wondering, because I was just sitting there for a second, like, how would I visualize that without it completely killing my brain? But yeah. Just
Okay,
curious.
so a cube.
Did you stab yourself in the face with your
my
A
math
cube
kit
has
in my eye.
x by x by x dimensions, and it says that the side length is decreasing at a rate of 1/2 millimeter per second. Okay, so how do I write that mathematically? The x is decreasing at a rate of 1/2 millimeter per second. Yep, so x prime, so that would be the rate of change of x. X is changing at a rate, so x prime, and you'd write -1/2. That's it. So, what's the moment we're looking at? What's the moment in question? The big moment. This is my line. When the surface area is 600. So, let's think about this. Maybe it might not be obvious. What does that correspond to in terms of x? So maybe we should start by just thinking about what's the surface area formula for a cube. I should just use S. I
So
think.
just 6x.
If you ever rolled some dice, you know,
Is this for B or is it still for A?
we're still on A. We're still, well, I guess we're still going to set up A and B at the same time, sort of. Because the moment that we want to look at in time, spoiler alert, it's when X is 10. Oh, no, not 10, is it? I'm sorry, root 10. No, I'm silly.
I'm silly.
No, it's 10. Sorry, it is 10.
Wow, what a
Silly,
spoiler.
silly.
Spoiler alert, It's when x is 10. So,
Is it true?
well, yeah, because, well,
know.
what I was trying to get
So
to
silly.
in sort of, I guess in a dumb way, was that if they tell you, hey, look at this moment in time when the surface area is this number, it's going to make sense to go, well, how do I quantify, how do I relate the surface area to x? So if you've rolled dice before, you know that the surface area, there's 6 sides to a cube. Each side has an area of x times x, so the surface area is 6x squared. And so let's figure out this moment then. If 6x squared has to equal 600, then x has to be 10. Does that clear it up maybe? Okay, so the moment we're concerned with is this, when x is 10. I'm just putting that on there because a lot of times they, capital T, they, give you the information you're looking for in sort of a roundabout way. They might not tell you exactly what x, the value of x is. Nice tabs.
Thank
Okay.
you.
S prime then would be 12x times x prime.
Yeah, so this is.
You guys feel okay about that?
second part. Yeah.
So notice that this derivative is going to depend on the size of x and the size of x prime. So we get 12 times 10 times negative 1/2. By the way, this is S prime at the moment when x is 10. This is pretty important notation because otherwise you're suggesting that S prime is constant, which is not. S prime changes all the time. So we get negative 60. What kind of units are we dealing with here?
Millimeters.
Square per second.
Square millimeters per second. So of course that's part B. That's the surface area part. But we kind of had to do that first because how else would we have known what x is? The volume is x cubed, x times x. So b prime is 3x squared times x prime. And then so b prime at the moment when x is 10, again, it's the same moment we're looking at. 3 times 10 squared times negative 1/2 gets you negative 150.
Yeah.
This time the units are cubic millimeters per second. The units work out because this would be millimeters squared times millimeters per second, which works out to millimeters cubed per second. All right.
What?
Was that